real exam questions. This is question 73 about strut and ties, and it will deal with a foundation block. The foundation block shown here, and all dimensions are in millimeter. It has the properties as indicated in the drawing. The concrete quality is 30 megapascal, the yield is 500 megapascal, and the total load is 550 kilonewton in ultimate limit state persistence. This load includes also the weight of the foundation block. The center of gravity of the compression strut near the column is at 100 millimeters, and near the piles, the two piles, it's also at 100 millimeters. Check the stress. The stress is in the knots, and check the compression strut. Determine the needed tensile reinforcement. So first we look at the foundation block. It's loaded with a force NED. It gives two reaction forces, and because of symmetry, RCD is equal, left and right is equal. The reaction force from the piles to the load NED. This indicates the point of gravity of the compression struts. We divide the load into two parts. This gives us, because this is the center, so it gives us this knot, the top knot. We do this the similar thing for where the piles are closing into the foundation block, and this is also the knot at the position of the pile. And when we connect those two lines, you see that we have now the two inclined compression struts. This is the force FCD, the normal force in the compression strut. This is the normal force in the compression strut on the other side. And they have an angle of theta, which gives you then the position of the tie in tension, which is FSD, and where the reinforcement will be positioned. So this is the mechanical picture of the different forces, and this is the geometry. So we start first to be sure, are we now in a D domain or in a B domain, or is it now resisting by bending or resisting by tie and strut method? So we check this. That means that the effective length must be smaller than 3 times the depth of the foundation block. The effective length is the total length minus 300 of the pile minus 200 of those two pieces where the at the outskirts of the pile. So this is 1000 smaller than 1200, so this is okay. So we are in a D domain. The effective depth of the foundation block, D, is then H, the total depth, minus the point of gravity, Y0, and minus the point of gravity at the bottom, minus 100. So D is 200 millimeters. The inclination of the strut, theta, Tanger's theta is then given by 4D divided by 2L minus A0. And when we put in some numbers, we find that the tangents of theta must be 0.44, or theta is 24 degrees. So this is quite steep, but it's still it's okay because it's bigger than 22 degrees. Now let's continue to calculate the different forces. The normal force in the column, NED, is 550. The reaction force in the piles, RCD, is half of it, which is 275 kilonewton. The normal forces, FCD, in the struts is, of course, the reaction force divided by the sinus of this angle. That's a sinus of 24. So we have 676 kilonewton left and right. And now the tension force in the tie is the reaction force divided by the tangents of theta, and it gives you 618 kilonewton. We will check now the different nodes. We start with the node which is in complete compression on the top of the bearing block, which is the load of the column meeting the two compression struts with their forces. For this node, the maximum allowable compressive strength is then equal to 17.6 megapascal, with alpha CC is here 1. The acting compressive strength on this surface is then equal to 550 divided by the cross section of the column, which is 200 by 200, and it gives you 13.75 megapascal. We check the stress on the other side. So it's given by this formula. It's 2 times 676,000 times the sinus of theta divided by 200 times 200. And it gives you 13.75. So on those two ties, we see now clearly that it is an hydrostatic situation. And this is what we should have as a result. 13.75 is smaller than 17.6, so this node is okay. Let's go to the pile nodes of the two piles. We have a stress, or we have a section here and a section there. The normal force of the strut is 676 kilonewton, and the contact on the contact side of the pile, it is 275 kilonewton, and the tension in the tension strut or tension tie is 618 kilonewton. So starting, we first start with the maximum allowable stress in a node where tension and compression is meeting. Then we know we have 0.85 times this value, and it gives you in total of 14.96 megapascal as admissible compressive strength. The acting compressive strength is, of course, just the pile, the foundation pile divided by the cross section, and it gives you 3.06 megapascal. And on the side of the compression strut, we have the total force times sinus of the angle times the cross section gives you also 3.06 megapascal. Both are smaller than 14.96, so this node is also fine. Now we will have to check the stress in the compression strut. The maximum allowable stress in the strut itself is 0.6 times this value, or 10.56 megapascal. The length of the strut, the S is D divided by sinus theta, is equal to 492 millimeters. And the cross section of the strut, that is not a problem, but we will use the simplified methods for the check of the stresses in the struts, because those struts start with a smaller cross section and goes to a wider cross section. So it's a little bit difficult on which cross section are we going to check. So we take a simplified method. It means that on the column side, the cross section will be equal to 49,272 square millimeters. The pile side, pile or the foundation pile side, there the cross section will be 221,000, and the cross section that we will take for the checkup is the minimum of 5/3 of S01 and 17/12 of the cross section S11. And we take the minimum, of course, because it gives you the highest value, and the minimum is 82,000. And the stress in the strut is then the compressive strength of the compressive force divided by the cross section gives you 8.25 megapascal. It's smaller than 10.56, so the compression strut is also okay. Now we have to define the reinforcement tie. The reinforcement is just the reinforcement, the tension force divided by the yield strength of the reinforcement. We need 1,421 square millimeters. The depth of the strip where we will put in the reinforcement is 100 millimeters. And the width of the strip, of course, is the width of the foundation block, which is 500 millimeters. So we prefer to put all the needed reinforcement in one layer over, nicely spread over the width of the foundation block. We first look, there are different possibilities, but now we just show you how things works. The total needed reinforcement we know, and now we will test it for a certain number of reinforcement with a certain diameter. So we take first diameter 32, and you see for a diameter 32, we need 1.77 rebars, or 2 rebars will be okay. Next, we do the same test with a diameter of 25. We need 2.9 diameters, so we have to round it up to 3 rebars 25. And for a diameter 20, we need 4.5, so we put 5 rebars. And last but not least, diameter 16, we have 8 rebars of 16, which is going to, which can give you a problem to put them all into one layer. So when we look at those figures, we see immediately that the best solution will be 3 bars of 25 with a total capacity of 1,473 square millimeters, because the others give you much more reinforcement. Finally, to sum it all up, the total force was 550 kilonewton. The forces in the compression strut was 676 kilonewton, and the tensile force in the tie was 618 kilonewton. The angle of the compression strut was 24 degrees, and the reinforcement was 3 diameters 25. We did not talk here about the minimum reinforcement in the total block, and we did not check the tensile stresses in the compression struts, because this compression strut has a smaller cross section on top than on the bottom, so they are fanning out, or they disperse. So, and this disbursement gives rise to tensile forces. It was not checked in this exercise.